How do we know what stars and planets are made of without ever stepping foot on them? That's what we're going to talk about today. Hi, this is Jill from the North Woods, talking about nature right outside our front door. Sometimes the nature is really high up there, and sometimes it's right outside our front door. But we're going to ask this question, and we're going to take a look at basically how it is. We've never walked on Jupiter. We don't ever go to stars. We don't have material from Pluto, and it's 4 billion miles away. How do we know with confidence that Pluto has methane, ice, and nitrogen frost on it? That Mars is covered with rust, iron oxide, dust, and that the deep blue on Neptune comes from methane gas in the atmosphere absorbing the red wavelengths? How do we know that? And how does anyone know that? Last episode, we talked about spectrometry and what it is and how science of reading light in a certain way is a detective type of mode where you're reading evidence. Every element leaves a fingerprint in light. Every specific wavelength we see that is being absorbed or being emitted, the patterns that we see out of coming thing, they tell us a story. They look a little bit like barcodes. If you've ever seen what spectrometry looks like, you get basically a band of light that is being emitted out of this object, and then there's lines in it where that absorption of that material or that wavelength is being absorbed and not emitting out of it. We saw how that principle allows you to take something like an engine and diagnose what's going on inside of a closed engine based on what kinds of bits and metals are inside of the engine, or how crime labs or packets of color, happen in a fire. We see or heard that helium was revealed to be in the sun 3 decades before anyone ever even found it on Earth, because we use spectrometry to give us more information about what it is. We're starting to take flights into outer space, but we haven't gone that far yet. The solar system itself is full of colors, and every one of those pieces of color is a bit of information to tell us what it is. We take a look at this, this particular moment. I think about the story I read about 1835. There was a French philosopher named Auguste Comte. And he sat down and he wrote what he considered to be sort of a definitive statement about the limits of human knowledge. And he was talking about the stars. And he said essentially that there's just some things we will never know a thing about. We can observe their positions. We can see how they move. But their physical nature, what they're actually made of, that's just going to be beyond the reach of humanity. And he meant it as a statement of scientific humility. We're just never going to know. And there's, true that there are limits to what observation can tell us. Stars are unreachable by us, at least right now. And without a sample, without like a specimen or a bit of material, how do we know what's in there? How can we analyze it if we can't put it in a flask and look at the chemistry behind it? How do we take something that's 93 million miles away and decide what it is that it's made of? But within 25 years, he was proved completely wrong. And it wasn't an accident, but instead what happened was a telescope got built that was finally able to see the surface of the sun. And with a fundamental insight about what kind of light was coming out of the sun was telling us more. There was two scientists, Kirchhoff and Bunsen. He's the Bunsen burner guy, decoded the dark lines in the sun's spectrum in 1850 and 1860. And what they identified wasn't just sodium and iron and calcium in the sun's atmosphere. They demonstrated something that changed the entire way we understand astronomy. The universe is not closed to us. It speaks to us if we know how to read it properly. And that's what they discovered. Comte's basically impossible question had an answer, and it had been sitting there in the sunlight the entire time. So we go back and take a look at our back door again, right? We want to talk about what's going on. Whenever we see an element, an element that when heated or energized emits a kind of light. Our fireplace, we get certain kinds of light out of it. Our light bulbs, we get a different kind of light out of it. And when anything is doing that, it's going to emit light at a specific wavelength. And that characteristic has a fingerprint. Sodium, as we mentioned before, has a very vivid yellow color. Copper is produced from a blue-green color that we see. Each element has its own signature colors. And there's a mirror of that too. Elements just don't emit a particular color. They also absorb other colors. So when light passes through a gas or an atmosphere, there are certain particular elements or characteristics of the light that are going to get removed from it. And those are going to be dark lines that we see in how we look at that. What comes out the other side isn't a perfect rainbow. It's a rainbow with dark gaps in it. And these specific dark lines at a specific point tell us exactly what's getting absorbed in the atmosphere of whatever it is we're looking at. And so there was a guy named Fraunhofer who was cataloging what he mapped, these hundreds of dark lines that were being suppressed or from the sun crossing, its light coming out of the spectrum. And he didn't really know what caused it. He just documented. I don't know why this is happening, but when I look at the sun spectrum, there's black lines here. I don't know what it means. And essentially, what it determined is he called them the D lines, B lines, H lines, K lines. And it took another generation to figure out, the sun's elements in the outer atmosphere were absorbing their own characteristic wavelengths as the light was passing on its way to Earth. And each dark line was announcing basically an element all by itself. And what's amazing is they found over 25,000 absorption lines in the sun's spectrum. That means that there's 25,000 individual gaps that where the elements have pulled various specific wavelengths out of the light. And those, approximately 75% of those, have been matched to known elements. The other 25% are still being worked out. And the story the sun is telling us isn't fully translated yet. We still don't know everything about it. But the same principle is going to be the same, that light passing through something is going to give us a fingerprint, and we can investigate exactly what that fingerprint is. If planets, themselves don't produce their own light, mostly they just reflect light outwards. Light from our own sun gets reflected out, and then that helps us understand a little bit more about them. But think about it this way. The light that gets reflected out from a planet is not exactly the same wavelengths as the light that goes in to the planet's atmosphere from the sun itself. So just think about it, our own planet, right? We get light from the sun. It comes in with certain wavelengths. And when we reflect that light back out, it's not exactly what the sun produced. When you look at our planet, it looks blue. It has other types of color, bandwidth, and gaps in it too. So it bounces off the surface. The minerals and ice and dust and gases absorb their own wavelengths and then travel back outwards. So if you had aliens looking at us through a telescope, they would experience a different set of wavelengths that we would have. It carries a record of basically what it hit in our own Earth's atmosphere. Spectrometry, it basically compares the spectrums of that, what the sunlight looked like before. If you were looking from outside our solar system, you would see, the sun, it has its own wavelengths, but when it leaves Earth, it has different gaps, different missing wavelengths, and those gaps are going to be the fingerprint of whatever it encountered on those specific planets. It helps us understand what other planets' atmospheres are made of. So if we move it back into our real world, let's talk about some various colors. So Mars is red. It's not orangish or brownish. It's a really remarkable color of red, and that is not because of what colors are being absorbed out of it, but because The planet itself is made of iron oxide. It's rusty. And the Martian surface has all this material on it, and it is rust. The entire planet is just covered in rust dust, fine, oxidized iron particles that coat every bit of the rocks and the soil and the atmosphere, every place in it. The iron oxide absorbs the blue and the green wavelengths. And so when you look at it, it's going to be a combination of that is what the planet is just built like. But every bit of blue and green is also being absorbed by the atmosphere there. The planet is broadcasting its own chemistry. And it goes further than just like the surface itself. The iron compounds form rust, obviously. The science can map across the surface of Mars differences in the compounds of Mars. Areas where iron material is a place where it met up with water, a place where it didn't have very much moisture. And so it gives a geologic history to us, telling us what's exactly going on. When we look at Venus, Venus is very bright in the sky. They call it the morning star, the first star you see at night. It's one of the brightest objects in our galaxy after the sun and the moon. It's so reflective, it can cast shadows on a night sky. It is actually, because of that brightness, it's a little hard to study here because some of those thick feature clouds almost hide everything. You can't see what's going on in Venus. It's basically cloud covered, but through spectrometry, we can get through those clouds in a way that telescopes can't. The spectral fingerprints that are coming off of Venus reveal an atmosphere overwhelmingly carbon dioxide. It's the same gas that, we breathe out, right? We breathe in oxygen, we breathe out carbon dioxide. And so it has trapped in heat. And so the surface of Venus hovers around 900 degrees, hot enough to melt lead itself. And the clouds themselves are composed mainly of sulfuric acid droplets, not water like our clouds, but it's sulfuric acid. And so Venus looks beautiful from a distance, the steady white gold light in the evening sky. But now we can actually tell what's going on. I think it's pretty amazing. Jupiter has that banded storm system that goes around. So if you look at Jupiter, it has bands on it, and then it has that big red storm on it. When we look at that, we make observations. We don't really, knew for a long time what was going on it. But now we know Jupiter's upper atmosphere contains ammonia gas crystals. It identified through spectrometry the absorption signatures of ammonia. And then throughout these cloud layers, the different cloud bands correspond to different altitudes, different compositions of atmosphere, the different chemical mixtures at different depths. The Great Red Spot is a long-standing puzzle for us all. The red actually comes from chemical compounds that are still trying to be fully characterized, but likely there's a lot of materials in there, molecules in there, sulfur compounds, and creates that intense chemistry that's going on. And so this centuries-old storm is still revealing information to us. Neptune is a deep blue, but it's a different blue than Uranus is. Neptune is one of the most striking colors that we see in our planet. It's this deep saturated blue that looks almost artificial. It's a very vivid against the black sky, but that's caused by methane. And Neptune's atmosphere contains methane gas, and it absorbs a particular signature, strongly taking away the red wavelengths. And so when the sunlight hits Neptune, the methane removes the red spectrum from it, and what we get reflected back to us is blue. Uranus has a similar methane atmosphere to it. It's roughly in the similar concentration too. But the reason that Uranus looks so different and pale compared to the rarely blue-green of Neptune is because, and this puzzled scientists for many years, is that Uranus has this atmospheric haze to it, that particles suspended in the upper atmosphere dilutes and muffles the methane signature. Neptune's atmosphere appears to be clear, and so that methane effect comes through potently, while Uranus is a little bit more hazy. So a similar chemical structure compared to, but a different result, I guess to say. And Pluto, a planet, of course, we've never landed on. We don't know much about it. We did a flyby in 2015 with the New Horizons spacecraft. But basically, it carried a spectrometer on board. And so that data was returned with extraordinary results. Pluto's surface has a distinct methane ice, nitrogen ice, and carbon monoxide ice. They have the carbon monoxide detectors, carbon monoxide, right? And it has its own spectral signature, each mapped in different areas of the surface. So there's a famous heart-shaped region that's on Pluto, and it's considered to be a vast area of nitrogen ice. We've never drilled for samples. We've never landed on it. We haven't even come close to it. But the spectrometer traveling past at 30,000 miles per hour was able to read the light that was reflecting from Pluto's surface thousands of miles away and assemble a chemical map of the planet. So for 85 years after its discovery, Pluto's faint blurry dot was the best our telescopes could do. But in a matter of a few hours, the spectrometry was able to turn the world into a mapped chemistry surface. It's really remarkable when you think about it. So for everything that we talked about, the spectrometry can tell us about composition. It can tell us about what things are made of, what light carries from going into a planet and then coming back out. And I think what's extraordinary about it is that if you even think there's something called the Doppler effect, and we're not going to get too much into this, but if you ever heard an ambulance, as it approaches, the pitch changes as it goes away from you. It might go, that's how sound makes a noise for us. But as it passes away, the pitch drops, and that's because the waves are being compressed as the source moves towards us and then stretches longer as it moves away from us. Light does the same thing. And so when a light source is moving towards us, the wavelengths get slightly compressed and shift towards blue in the spectrum. When it moves away from us, they stretch and shift more towards red. I'm not going to get into it, but you could want to Google it. It's called blue shift and red shift. And that amount of shift tells exactly how fast an object is moving towards us or away from us. And that gets interesting when we're looking at planets and stars. We can see that there's specific dark gaps at wavelengths. We can measure those shifts and where they should be and where they actually are. Is the planet rotating on one side as it's moving towards us? Is it on the other side and moving away from us? These spectral lines give us a slightly nuanced blue shift or red shift. And so then scientists can even measure how fast the planet is rotating, the speed that the planet is turning, and it gives us a bigger application. So now we can even see other stars, what their gravitational pull is like. Is it causing a star to wobble slightly as it's coming towards us or going away from us? There's a tiny wobble that Jupiter makes our sun wobble back and forth at just a little bit at roughly 30 miles per hour because Jupiter is so massive. And our spectrometers today are able enough to detect it. In 1995, astronomers used this technique of the wobble method so that they can confirm, it's also Doppler spectrometry, to confirm the first planet orbiting a sun star was called 51 Pegasus b. And it was a discovery that fundamentally changed how we understood how planets' systems were formed. These thousands of exoplanets have been discovered, and we're able to watch their spectral lines shift back and forth. Beyond the wobble method, there's another technique that gets even closer to what we've been talking about in this episode. It's called transit spectrometry. That's when an exoplanet passes in front of a star. Exoplanet is just a planet that's in the atmosphere. So think of it this way, that if we passed in front of our sun and someone was looking at us in a telescope, they would see our atmosphere and the light passing directly through it. When that happens and it passes through that starlight, a tiny fraction of the total light, the planet's compound is compared to the sun. and for a very sensitive spectrometer to detect the gases that it had passed through differently than the gas of the star that was passing light directly to us. So we've been able to detect whether things have water vapor, carbon dioxide, methane, sodium. For those very sensitive moments, we can sit back and figure out what exactly planets are composed of for places that we can't see, orbiting stars whose lights have been traveling for all this time. The photons are passing through these atmospheres for a split second and giving us a fingerprint of what's actually on that planet. What scientists ultimately are looking for is as our sensors become more and more sensitive, we're looking to see more chemical fingerprints. Is there oxygen on that planet? Is there enough oxygen on that planet that could support life? Are there organic molecules on that planet? And that's how we tell. If you ever seen those news headlines where they say, oh, we found a whole water world. I think we found a whole water world. That's how we know. Boy, so our solar system is one of color. Our whole universe is of color. And those colors tell us about those planets, whether it's the red of Mars that is rust forming on all the rocks, whether it's the deep blue of Neptune, which is methane filtering out the red light, the bright star of Venus, which is sulfuric acid clouds that's reflecting the sunlight directly. From a distance, they're beautiful. But essentially, that idea that we can now learn something that we thought in 1835 we would never know a thing about. And today, we're reading the atmospheres of planets, stars, light years away, seeing fingerprints of whatever is going on in the chemistry of those particular places. And it comes from that same instinct that light is just not light, it's a message. And once you know how to read it, the universe is a lot less closed off than it appeared to be. Next time, we're going to bring it back down to Earth, and we're going to talk about water and lake and other types of methods that we can use right here around us. Thanks so much. I appreciate you watching. You can leave a comment right here if you're watching this on a video channel. You can email me at jill@startwithsmallsteps.com. I'd love to hear from you. Thanks so much for watching, and have a great week.